Now we are gonna to studying measuring nuclear decay. You can imagine if you are studying a sample of radioactive material, you have to know the atoms in the material are decaying into other types of atoms. Now, the question is, how many of the unstable parent atoms remain after a certain amount of time? We will answer this question in the end of lecture. In the beginning, you have to know in 1898, Marie and Pierre Curie discovered two new elements, an unknown element before. The two elements, polonium and radium, both of which were radioactive. And we already know Marie and Pierre Curie were specialists in studying the radioactive elements. They were awarded the Nobel Prize in Physics in 1903 for their studies of radioactive substances. The decay constant indicates the rate of radioactive decay. When we have a sample contains n radioactive parent nuclei at some instant, the number of parent nuclei that decay into daughter nuclei delta n in a small time interval delta t is proportional to n, like these equations. Now delta n daughter nuclei, n parent nuclei. The negative sign signifies that n decreases with time, that is delta n is negative. The quantity lambda is called the decay constant. Its value for any isotope indicates the rate at which that isotope decays. This means the isotopes with a large decay constant decay quickly, and those with a small decay constant decay slowly. Now we call the number of decay per unit times is called the decay rate. You can define the decay rate, the number of decay per unit time minus delta n over delta t. The decay rate or activity. The decay rate or activity of the sample. Now the activity equal minus delta n over delta 2 equal lambda n. The activity of a sample equals the decay constant times the number of radioactive nuclei in the samples. Okay. The SI unit of activity is the becquerel. The unit is becquerel in the System International. One becquerel is equal to 1 decay over second. The Curie, Ti, which was the original unit of activity, the Curie, the original unit of activity, is the approximate activity of 1 gram of radium. 1 Curie is equal 3.7 multiplied 10 power 10 becquerel. After we recognized parent nuclei and daughter nuclei, we will move to definition half-life. Half-life, the time needed for half of the original nuclei of a sample of radioactive substance to undergo radioactive decay. And the half-life measures how long it takes have a sample to decay. The half-life written as T half. The half-life, we can define the half-life of a substance is the time it takes for half of the radioactive nuclei in a sample to decay. Conceptual challenge. Decay series, these are questions. Suppose a radioactive parent substance with a very long half-life has a daughter with a very short half-life. describe what happens to a freshly purified sample of the parent substance. You can answer by this way. The parent substance will decay very slowly. Many of its nuclei will remain and decay for a length period of time. As soon as some of its nuclei have decayed, the daughter nuclei will decay rapidly. This is the answer for question number 1. Number 2, probability of decay. The more probable the decay, the shorter the half-life. Explain this statement. This question is very important. As the probability of decay increases, the amount of nuclei that decay per unit time increases. So it takes less time for the sample to decay. Answer question number 2. Now, the radioactive nucleus, radium-226-88, has a half-life of about 1.6 multiplied 10 over 3 years. Although the solar system is approximately 5 billion years old, we still find this radium nucleus in nature. Explain how this is possible. The answer: other element with longer half-life decay to 88, radium 226, 88. Now, substances with large decay constants have a short half-life. Pay attention on this information. Now, the relationship between half-life and decay constant is given by the equation below. A derivation of this equation is beyond in the end of the book. Logarithm 2 equals 0.693. This equation used to solve the problem. Consider a sample that begins with n radioactive nuclei. By definition, after one half-life, n becomes half n. Radioactive nuclei remains. After 2 half-lives, half of these will have decayed. So, fourth n radioactive nuclei remain. After 3 half-lives, 8th n will remain, and so on. Let's take an example about the half-life. The half-life of the radioactive radium-226 nucleus is 5 multiplied 10 power 10 seconds. A sample contains 3 multiplied 10 power 16 nuclei. What is the decay constant for this decay? First question: how many radium nuclei in carriers will decay per second? Number 1, we have to analyze the questions. The given half-life equal 5 multiplied 10 power 10 second, and the number of nuclei equal 3 multiplied 10 power 16, unknown lambda, and activity. We have to choose an equation or situations to find decay constant. Decay constant is unknown. Half-life equal 0.693 over decay constant. The number of nuclei that decay per second is given by the equation for the activity of sample. We have to calculate lambda rearrange the equation to isolate the unknown from the first equations. Substitute the values into the equations and solve. Lambda equal 0.693 over half-life. Lambda equal 1.4 multiplied 10 power minus 11 second power minus 1. Second step, the activity equal lambda times n equal 1.4 multiplied 10 power minus 11 second power minus 1 multiply 3 multiply 10 power 16 divide 3.7 multiply 10 power 10 second power minus 1 over Curie. The activity equal 1.1 multiply 10 power minus 5 Curie. Always pay attention to units here. The activity is divided by the conversion factors 3.7 multiply 10 power 10 second power minus 1 over Curie to convert the answer from becquerels to Curies. We have a question, some questions. So now we will answer the questions. Number 1, the half-life of polonium 214-84 is 164 microseconds. Polonium 214 sample contains 2 multiplied 10 power 6 nuclei. What is the decay constant for the decay? How many polonium nuclei in Curies will decay per second? The answers? You have to get these answers. Half-life equal 164 multiplied 10 power minus 6 second. Convert to second. Number of nuclei equal 2 multiplied 10 power 6. Put the equations. Lambda equal 0.693 over half-life. Substitute in the equations. You will obtain lambda equal 4.23 multiplied 10 power 3 second power minus 1. Now what is the activity? Activity equal lambda times n. Substitute and divide 3.7 multiplied 10 power 10 second power minus 1 over Curie equal 0.23 Curie. Number 2, the half-life of bismuth 214-83 is 19.7 minutes. A bismuth 214 sample contains 2 multiplied 10 power 9 nuclei. What is the decay constant for the decay? First question, how many bismuth nuclei in Curies will decay per second? You have to get these answers. Half-life equal 19.7 minutes. Number of nuclei equal 2 multiplied 10 power 9. What's the equation? Lambda, and substitute in the equations. After that, calculate the activity. Activity equal lambda times n. Substitute in the equation, you will find 3.2 multiplied 10 power minus 5 Curie. Number 3, the half-life of iodine 131-53 is 8.07 days. Calculate the decay constant for the isotope. What is the activity in Curie for a sample that contains 2.5 multiplied 10 power 10 iodine? 131 nuclei. You have to get these equations. Put the information and substitute in the equation, you will find these answers. Number 4, suppose that you start with 1 multiplied 10 power minus 3 gram of a pure radioactive substance, and determine 2 hours later that only 0.25 multiplied 10 power minus 3 gram of a substance is left and decayed. What is the half-life of this substance? You have to get 1 hour. Initial mass equal 1 multiplied 10 power minus 3 gram. Time 2 hours. Final mass equal 0.25 multiplied 10 power minus 3 gram. Put the ratio between final mass and initial mass. You will get quarter. 2 multiply quarter equal half. So we know that 2 half-lives have passed in 2 hours. Half-life equal 2 hours divide 2 equal 1 hour. Last questions. Radon 222 86 is a radioactive gas with a half-life of 3.82 decades. A gas sample contains 4 multiplied 10 power 8 radon atoms initially. Estimate how many radon atoms will remain after 12 days. You will get these answers. Half-life equal 3.82 days. Number of nuclei equal 4 multiplied 10 power 8. 12 days divide 3.82 days equal 3 half-life. Half times half times half equal 1 over 8. 1 over 8 multiply 4 multiply 10 power 8 equal 5 multiply 7 atoms. Estimate how many radon nuclei will have decayed by this time. You have to get these answers. Indicate equal n minus n remaining. Indicate equal 4 multiplied 10 power 8 atoms minus 5 multiplied 10 power 7 atoms. Indicate equal 3.5 multiplied 10 power 8 atoms. If you want to study a decay curve plot. A decay curve is a plot of the number of radioactive parent nuclei remaining in a sample as a function of time. This is the answer of question in the beginning of the lessons. After each half-life, half the remaining parent nuclei have decayed. What's here? The blue spheres are parent nuclei, carbon 14. And the red spheres are daughter nuclei, nitrogen 14. Notice that the total number of nuclei remains constant, always. 8 becomes 4. 4 becomes 2. 2 becomes 1. N, half N, quarter N, eighth N. It's here, the blue sphere, red spheres, Now we'll explain living organisms have a constant ratio of carbon 14 to carbon 12. The reason? They continuously exchange carbon dioxide with their surrounding in the space. The carbon 12, which does not decay, provides an approximate date as to when the organism was alive. We get the ratio while the number of carbon atoms continuously decreases over time. Always you have to know the number of carbon atoms continually decreases over time. This is a graph between number of parent nuclei, remaining nuclei, and half-life. We want to answer some question, explain the main differences between alpha, beta, and gamma decays. We can answer. In particles are emitted, in electrons or positrons are emitted, in photons are emitted, in a new element is produced, in energy is lost. Now we had finished section 2, chapter 22, section 2. The other questions is homework. Thank you so much.